Hi, so our next talk is from Aldec by Ian Gibbins, but he'll also be supported by Christoph, and they'll be talking about revealing what's not visible with simulation. Ian is a chartered engineer from MIET with 30 years experience in ASIC and FPGA design, initially working in R&D and later consulting in mobile communications. He has spent 15 years in customer sales and support. Ian joined First EDA in 2006, where he has technical responsibility for a broad range of verification and validation solutions, including Aldec's class-leading portfolio. Christoph joined Aldec in 2001 and was a key member of the team that developed HES, Aldec's FPGA-based co-simulation and emulation technology. He has worked in the fields of HDL IP core verification, test bench automation, and design verification with DO254 compliance. As a technical support engineer and now manager, Christoph has practical experience and a deep understanding of co-simulation, emulation, and prototyping, as well as hardware tools training skills. So we're going to hand over to you now. Please, Ian.
Thank you, Mike. Hi, everybody. So we're going to talk about debug with emulation. So I'm going to start with just saying what really what emulation is. So it's just a combination of hardware and software where the hardware employs use of FPGAs and programmable interconnect and control hardware and software to support the operation of the emulated design as a hardware component operating in real time. And the use of hardware to emulate a system as fast as possible relative to real time is just becoming increasingly popular and more affordable. So, why emulation? So even though simulation runtimes have afforded gains through computing advances, with processor speed, simulation, architecture, the irony is that these advances can't be simulated long enough to find crucial bugs in time to market. And also simulation requires test vector development, which is costly and difficult, and the verification also depends on test vector correctness. And certain applications, have to be verified in real time with, human sort of interaction, such as audio and video. And emulation that's connected to actual hardware can run, real diagnostic code, operating systems and applications. And with real designs, real chips, internal probing, isn't possible once the chip's been fabbed and placed in a system, but can be possible using emulation. So let's go on to look at some of the essential elements to debugging in the hardware environment. So for efficient debugging, there are a number of techniques available. We've got debug probes that capture some internal signals and save those on the host computer in order to view on a waveform. Breakpoints and triggers. Difference here, breakpoints will stop the emulator when some event happens, whereas triggers are used for sampling debug probes. Clock control, that allows the emulator to be frozen or moved on step by step or a specific number of clock cycles. And true RTL debugging. So this is important because some problems exist when we're capturing data in hardware and it doesn't correlate with the RTL design. So it's important that this is supported so that signals captured from the hardware will match the names in the RTL source code. And memory visibility, so that allows the viewing and changing of memory data in the emulator. And before synthesizing a design, an analysis will be run to find what we call basal signals. And the basal signals are those that are essential for debugging, and they have to be captured from the hardware in order to provide full visibility. And then a kind of hardware debug algorithm can be used to expand these basal signals to give full visibility. So basically, flip-flop and memory signals are captured, and then the combinatorial signals can be computed. So let's look at the debugging techniques in more detail. So we're going to look at debug probes, which comprise static probes, and these are these are signals that are identified before the synthesis and are captured during the emulation in an embedded logic analyzer. So this is something similar to Xilinx chip scope. Dynamic probes, these use the Xilinx readback tool to capture the state of the design, and the hardware debugging algorithm expands these to full visibility. And with the dynamic probes, the signals can be chosen at runtime, whereas static probes, they're chosen during the setup process. So if you want to change static probes, then the design has to be resynthesized, although with dynamic probes, this you don't have to do this, can be done at runtime. So although they provide good visibility, it does come as a cost of speed. So the system clock is slowed down with dynamic probes. And the kind of methodology is to use the static probes to hone in on a problem area, and then dynamic probes would be then used for detailed debugging. With the debug probes, it's important to have a true RTL view. So the data that's captured from the probes is actually stored in kind of simulation-friendly formats, and the signals will be saved exactly as they are in RTL source code. And this is actually achieved with automatic RTL code instrumentation before synthesis. So this ensures that during synthesis we don't prune or remove signals that will allow the support of the dynamic probes and the RTL correlation. And the image here just shows our emulator connected to a host via the PCI, which is used to acquire the data. So talk a little bit more about static probes. So as mentioned, the static probes are similar to Xilinx chip scope, which is like an on-chip logic analyzer. So you have groups of probes which are provided up to 16 groups, and each group contains 16 kilobit of probes. And so at runtime, one of those working groups can be selected for emulation. And the signals are captured and transmitted via a common bus, which is transmitted down to the local host computer. Depending on the memory storage required, the verification manager can free up internal RAM blocks and allocate them to static probes. These are these little debug agents. And there are a few ways that we can store the samples. There's a continuous node drop-off mode. This is where samples are captured on every clock and stored in a local buffer. And if the buffer becomes full, then the debug agent requests to halt the emulation in order to flush the buffer. So this can cause the emulation to be slowed down, and obviously stop the clocks. So we've got with time windows, and so to avoid the emulation slowdown, time windows can be used, which means that you can specify how many samples will be captured by the buffer following the occurrence of a trigger. So therefore, a limited number of signals are saved in the memory. Okay, I think I was at I lost at storage expression, but so yeah, storage expression gives you the possibility to make a filter for these probes to qualify which signals are saved into the buffers. There is also multiple clocks in. If you've got multiple clocks in the design, then it is possible to choose which clock to use as the sample clock, and you can do that at runtime, and that obviously will influence how fast the emulation runs. And so all the results are saved in kind of simulator-friendly formats, and with RTL names and hierarchical paths being preserved. So in order to get our samples and our signals, we need triggers and breakpoints. So the on-chip logic analyzer gets these by setting up triggers and breakpoints, and this is controlled by the verification manager. So it's similar. The triggers are similar to static probes. The difference being that of the 16 groups that you can have, you can have up to 256 bits. And whilst this is a smaller capacity than static probes, triggers are just used to trigger expressions, and so fewer data is needed. And once the trigger group is defined, you can start building the expressions, and there are kind of basic to advanced expressions, basic equals, not equals, to Boolean trigger expressions, which is checked for a current state on a clock cycle. Sequence expression, this will span over multiple clock cycles, and that's used in conjunction with the Boolean expression. And there's a trigger event counter that allows debug to occur only after a number of certain events have occurred. And then we've got breakpoints, which are built from the same trigger group setup, and they allow the same expressions as triggers, but they're defined independently and used to stop the emulation clocks at the event. So moving on to dynamic probes. So these are used in conjunction with static probes. So as we've said, static probes usually hone in on the issue, and then a breakpoint set to stop the emulator. Then the dynamic probes can be enabled. They give you full flexibility of what you want to debug. You can select the signals and run the emulations with dynamic probes. They will be slower, but you'll be able to run the emulation at full speed until the breakpoint. Then you can start to select the dynamic probes and then move along at a slower pace. The dynamic probes are created via the Silence readback tool, and once captured, samples are sent over the PCI to the host. And with dynamic probes, it's possible to create breakpoints, but they can be slow because they're not checked in the hardware. They're checked on the host computer. So in order to look for a breakpoint, the data needs to be sent to the host. Hence, it's a slow process. And you have to specify the time in which to check for the breakpoint. So, for example, you have to, if you check for a breakpoint condition every 1,000 clock cycles. So this type of breakpoint can be useful for slow changing signals, but not for fast ones. It's possible to have a configurable sampling clock. Slower speed means that less signals are sampled, but the emulation will be faster. And again, the true RTL view is supported with dynamic probes. There's also standard memory visibility, which is, again, it's a pretty standard function. The data can be displayed in different formats with different radix. ASCII format view is possible. The main advantage with the memory visibility is that the data can be changed. So, for example, if you're running a SoC with an embedded chip running some software, you can build the image of the software on the host computer and then upload that image using the debugger. So the hardware debugger tool is basically a manager environment to enable the debug setup, the selection of the static and dynamic probes. It provides a GUI for all the debugging features and includes a TCP interface from the emulator to the host, so the hardware debugger can be run on a different computer connected to the network. So you can run it from your own and debug from your own desktop, and scripting commands for automation. And something else that's useful and available is a debug API. So as well as providing the hardware debugger, an API is possible for debug. And the API it's a C++ API which integrates to the design test bench, so that the test bench can check memory and configure breakpoints. So in essence, the test bench can be used instead of the hardware debugger. And the API provides access to all the debugging features, so it's very convenient for creating self-checking test environments or regressions. Another available interface is embedded software debugging, and software interface is very often used when the emulator is used with a virtual platform. So the virtual platform is used to model the SoC and is usually used for standard components such as the ARM processor or standard peripherals. But in a lot of projects there are some custom IPs, and these custom IP cores are usually available as RTL source code, and could be run in a simulator or an emulator, but there might not be a virtual model for the virtual platform. So the interface is needed to connect to the virtual platform to the emulator, so that you can actually get to the IP that's running in the emulator. So if you do have a processor that's running the virtual platform, then you use the interface from the vendor that supports the virtual platform. But if you have the case where the processor is running in the emulator, then you can actually connect to this using the interface which is running the processor. And the common interface for this debug is the JTAG, and a virtual JTAG transactor has been developed in order to be able to connect to this debugger. And the virtual JTAG transactor connects to the JTAG ports of the design of the IP that's running in the emulator. And then on the software side, it provides the TCP interface for the debugger. So it's possible, for example, to connect to an ARM or GDB. So we talked about a system for hardware debugging, and just like to share a couple of slides on an actual AUDEC system that supports this, which is the HES system. And HES stands for Hardware Emulation Solutions, and there are several components that make up the complete solution. So we've got FPGA prototyping boards utilizing the Vertex 7, and currently testing the ultra-scale FPGAs for the hardware platform. There's a design verification manager which controls all the interfaces and different tools depending on the tool flow. For example, the transaction level interface or bit level interface SCIMI is supported, which is the Accelera standard, and with SCIMI it's possible to support system Verilog, UVM, System C, C++, and at the bit level we support the VHPI and PLI interfaces. And we've got the comprehensive hardware debugging tools, which we've actually talked about in the presentation, and there's also a library of verification IPs which contain transactors, monitors and speed adapters, and these are usually licensed separately with the system. And here's just a shot of some of the FPGA boards, and good nice sexy shots. And as I said, coming soon, we've got the Xilinx UltraScale board, which supports up to 633 million gates. And as far as applications and interfaces with HES, the different interfaces allow connections to different environments. So using SCIMI and VHPI or PLI, a system can be connected to simulators so this is simulation acceleration. Having the SCIMI and transactional level models wrappers allows connection to the System C environment, which is co-emulation, and possibility to connect to different platforms such as the ARM virtual platform or the Open virtual platform, or even virtual models that are System C or C++ based. So basically any application that can be developed that supports SCIMI interface will act as a virtual peripheral or model. We've got in-circuit emulation, or ICE, which connects the emulator to a design with some real device or real peripheral. So for example, a real USB device or Ethernet network, or HDMI, to show image data from the emulator. And due to the difference in speed, the emulator being slower than the real device, so we need speed adapters to actually connect to the real device. So when the emulation is run, the environments need to be able to debug hardware. So interfaces are provided via TCP/IP. So the application is run on the host, and you can use TCP/IP to connect to the emulator. What we've seen as well, talked about, is another methodology is to debug the software that's running on your design, due to the SoC being a combination of hardware and embedded software. So the software debug is supported through the JTAG port or VJTAG. So to conclude, we've talked about how emulation is becoming more popular and affordable in the design verification process, and how emulation can increase the visibility of bugs in the development of an SoC that simulation couldn't find, in the time to go to market. Additionally, we've seen techniques that with comprehensive methods that exist to debug hardware, and most importantly give full signal visibility and correlation with your RTL design. Thank you very much.
Thank you, Ian. Thank you. We've got a couple of minutes if there are any questions. Any questions online? Any questions? No, so I think we'll just go to the final slides to wrap up. Thanks again, Ian. Thank you very much. Thank you.
Okay.
So just a final wrap up to say thank you to our sponsor.